What is going on, everyone? Welcome back to another lecture. We are still going to continue the chapters of inner product spaces, and that is going to be the topic that we're going to be discussing on this video. The last lecture, we talked about lengths and dot products and angles between two vectors, and so that is that is gonna be something that you're gonna later find out on what it actually means. So we're just gonna go ahead and jump straight to it. So in general, when we talk about inner products, we are talking about a specific type of set that is within a vector space. And so last lecture, when we discussed about the dot product, well, the dot product is essentially an example of an inner product. So in other words, the dot product is an inner product, and the inner product is like something much more bigger. And the dot product, it's more formally known as the Euclidean inner product. And so the notation, it's one that you already known and seen. It is just u dot v, with u and v being vectors. So in general, the inner product of a vector space, its general notation is u comma v, in which the u and v are in angle brackets. And so a vector space V with an inner product is called the inner product space. Whoa, who would have thought? For it to be an inner product, it must follow 4 sets of axioms. It's just pretty much similar to a vector space. So if you recall, for a set to be a vector space, it has to obey 10 axioms. But in this case, it's going to be 4, which is much more nice than 10. And so we're going to discuss about the axioms of the inner product. So before we talk about that, we need to establish some given things in this axiom. And so we're going to let u, v, and w be vectors in the vector space V, and let c be any scalar number. And so our first axiom that it must obey is that u comma v must be equal to v comma u. The next one is u comma v plus w must be the same as u comma v plus u comma w. And then the third one is the scalar. So some scalar c multiplied by u comma v is equal to that scalar multiplied by u comma v. And then lastly, the last axiom that it must obey is that the inner product of v comma v must be greater than or equal to 0. And if it is equal to 0, that will only mean that the vector v is 0. And so these are the 4 simple axioms that it must obey. If any, and like the same thing with the vector space, if any of them fail to abide one of these 4 axioms, then it is not considered an inner product. And so these inner products have some properties. Of course, a lot of things have properties. And so again, we're just going to let u, v, and w so be vectors in the vector space of V, and c be any scalar. And so the first one is the inner product of 0 comma v is the same thing as the inner product of v comma 0, which is 0. The second one is it's pretty much the same one as the second axiom. So the inner product of u plus w comma v is the same thing as the inner product of uw plus the inner product of vw. And then the last one would be the scalar property. So the inner product of u comma c v is the same thing as the scalar c multiplied by the inner product of uv. And so now that we discussed about the inner product, which is a much more general thing of the dot product, we can pretty much redefine the norm, distance, and angle of vectors in a more, I guess, general way. And so before we do that, we're gonna establish our definitions of letting v and w be vectors in a vector space V. And so what that means is that the norm, or the length, of V is given by, again, the two, this absolute values of V is the same thing as the square root of the inner product of V comma V. And the distance between v and w is given by dv dot w, which is the same thing as v minus w. And then lastly, the angle, well, yeah, kind of. The angle between two non-zero vectors, v and w, is given by the cosine of theta is equal to the inner product of those two divided by their respective magnitude. And the angle is between 0 and pi, or 0 and 180 if you're using degrees for some reason. And then lastly, which is not much of a definition, but it is a good observation, is that if v and w are orthogonal to each other if their inner products is equal to 0. And so these definitions they're pretty much the same thing as with the dot product, but the only difference is that we're replacing the notation to a more general notation. And so now we are going to talk about orthogonal projections or orthogonal projections in inner product spaces. And so we're gonna let vectors, or we're gonna let v and u be vectors in the vector space V. And so if v is a non-zero, then you can orthogonally project onto v. And so what that means is that if v is just any vector but 0, you can have the second vector u, which has to be non-zero, have a projection on v such that it is orthogonal to vector v. And so to find the projection of v, it is simply given as projection of subscript vu is equal to the dot product of u and v divided by the dot product of v to itself and multiplied by the vector v. And because the u dot v over v dot v, it gives you a scalar, we can just substitute that in to just being a. And to have like a more visual representation is we have here on the left side, we have the vector v just being extended, and then some vector u that is theta degrees from v. And so we can see here is that this vector u can make a projection on v that is the like yellow orange line, and it's given by just the formula that I've shown you here. I will show the derivation on like where it comes from, and that will be on a linear shorts video, so be on the lookout for that. As for now, you're gonna have to just like take it as is, but yeah, the left side is only for when alpha is greater than 0, so that means when cosine is less than, when cosine's less than pi over 2, I believe. Yes. And then the one on the right is pretty much the same thing, and that's the only exception is when a is less than 0, so that means when the angle theta is greater than pi over 2. And so the orthogonal projection, the more general formula, is given by the projection of v on u is equal to their inner product of u and v over the inner product of v to itself, and then multiply those two, multiply that scalar by the vector v. And another cool thing about it is that if v is a unit vector, then the projection of u is essentially just the inner product of uv multiplied by the vector v. And so another thing with with these projections is that the orthogonal projections has like, or the distance between the orthogonal projection and u is given by the distance of u and the orthogonal projection, and it has to be less than the distance between u multiplied by some scalar c times vector v, such that c is not pretty much a or yeah, c is not the inner product of uv over v by itself. And yeah, and this makes sense because we mentioned that if two vectors are non-zero, one can be a projection orthogonally projected to another, and if one is orthogonally projected to another, that means that it can be written as a scalar of that vector that's being projected on. And so what that means is that if we have our distance between the projected vector on u and some scalar times v on u, then the distance between the scalar and v on u must be greater than the distance between u and the projection. And so I will have like a visual representation on when we start working on the examples, if that confuses you. But other than that, this is the end of this lecture. We are going to do examples on like finding the inner product spaces, and we're gonna put in some calculus into this because I feel like that is going to be very important as you move further up the levels of mathematics. And so we're gonna have some examples that involve calculus, and then showing if something's in inner product or not, and then finding the inner products, and then as well being a lookout for any linear shorts for the derivation of the orthogonal projection. But other than that, I will see you in the blackboard.